First part of today, we're going to be working on independent and dependent events. We have talked about them a little bit, and the words themselves make a little bit of sense. Two events are dependent when the outcome of one event affects the outcome of the other. So for example, let's say you have a deck of cards, you're trying to draw a card, and then you don't replace it. What happens then is the probability of the first card is one number, and then the probability of the second card is changed because you didn't put that one card back in the deck. So now you have fewer cards that you were drawing from. So those events would be dependent because it depends what you get on the first card, what's going to give you the probability for your second card. Our other kind is independent, which means what you do for the first one does not affect what happens in the second one. So like pulling a card from a deck and spinning a spinner. No matter what you get on that card, it's not going to affect what you would get if you spun the spinner. So those would be independent events. They're not connected in any way. So for exercise 1, we are going to classify each of the following scenarios as having events that are dependent or events that are independent. So A, a person pulls a red marble out of a bag that has 5 blue and 7 red and does not replace it. Then a person pulls another red marble. Is the probability of pulling the second red marble dependent on pulling the first red marble out? Yes. Why?
Because if you pull out the first red marble and you leave it out, then that means that other people are pull it out.
Yes. Because when you
There's a better way to explain that.
don't replace the first marble, you have fewer marbles to choose from the second time. So the probability the first one's red would be 7 out of 12. However, the probability the second one is red would be 6 out of 11. So it would change because you've pulled the red marble out the first time. All right, B, a person flips a coin and notes that it comes up as a heads. Then the person rolls a standard 6-sided die and notes that it comes up as a number less than 3. Is the probability that the number came up less than 3 dependent on getting a head on flipping the coin? Explain. No. Why? No, because there isn't a connection between the two events. So there's no way flipping the coin is going to change what you could possibly get on the die when you roll it. So those are independent. One can happen and the other one can happen, no connection. So the idea of independence is one that comes fairly naturally, but is important in order to see if there are associations among two events. So let's develop a tool to help us test dependence. So we're going to come up with 2 different ways that you can figure out if things are independent or not. So here we have a spinner. It's spun and its outcome is noted. We're going to let letter E be the event of getting an even. And then the letter P is going to be the event that you get a prime number. And the letter L is a number less than 5. So E is even, P is prime, L is a number less than 5. No. Find the following probabilities. So probability of getting an even. This one's pretty easy. How many even numbers do we have on our spinner? 4 out of how many numbers total? So it'd be 4 out of 8. We reduce that to 1/2. So the probability of giving an even would be 1/2. So now B is the probability of getting an even given that the outcome was a prime number. So this goes back to what we were doing last class. So probability of even given that it was prime would be the number that are even and prime over the number that are prime. I knew to go with the numbers instead of the probabilities of even and prime over the probability of prime because we know what the sample space is. We know how many numbers are in the sample space, so you want to just go with the numbers this time. So how many numbers are even and prime? Don't all shout out at once. 2. 2 is the only one that is even and prime. So there's one of them. How many prime numbers do we have?
5.
False.
Can you talk about what prime number is?
It's only
I'm sorry, I remember.
only that number in itself.
It has 2 factors, a number and 1.
Sorry, guys.
So for 2, it's 2 times 1. That's the only way you can get a 2. So it's prime because there's only 2 numbers.
There's 5.
There's 4.
1 isn't prime.
1 is not a prime number because it's got 1 factor. 1 times 1. It's the same number. There's 1 factor. So it is not prime.
It's 4.
It's 4. Good job. So the probability it's even given that it's a prime number is 1/4. So C, the probability of getting an even given that the outcome was a number less than 5. So the probability of even given that it's less than 5 would be the number that are even and less than 5 over the number that are less than 5. So how many are even and less than 5? 2. How many numbers are less than 5? And that reduces to 1/2. So which event does E depend on? P or L? How can you tell? And what is a reasonable test? So, you see how this one and this one are the same? Are A and are C, same probabilities, 1/2. So that means those 2 events are independent of each other because the probability of getting an even does not change even when you put it out of the number that are less than 5. It is still the same probability. So those events are independent of each other.
And the probability of a prime number is dependent on the amount of them.
So E depends on P. It depends on the prime because the probabilities are different. So those 2 are dependent on each other because their probabilities are different. We had a 1/2 and a 1/4, not the same. So a reasonable test. Probability of any event, I'll just use A for right now, given another event, I'll use B, has to be equal to the probability of just A. That's how you know it's independent. If those 2 things are equal, like it was in A and C, then those 2 things are going to be independent. If your probabilities are different, that's when they're dependent. One does depend on the other one. So here's that rule that we just wrote on the front. Doesn't matter which way it goes, probability of A given B has to be the same as probability of A. Or probability of B given A has to be the probability of B. It's always whatever that first letter is the one that's by itself to get you your independence or your dependence. So let's take a look at our survey. We're going to practice finding out if things are dependent or independent. We have a survey of 57 6th graders. It was done to determine which subject was their favorite. The results are shown in the table below, sorted by gender. So we got male, female, math, English, social studies, and science. Does it appear, based on the data in this table, that the preference for math as a favorite subject has dependence on a student's gender? Show the analysis and explain your findings. So, let's figure out. What is the probability that a person picks math?
Well, you do whatever the math total is over.
Okay, so what is the math total? Out of? And since we're going to be comparing some things, let's turn this into a decimal. So go ahead, use your calculators, divide 18 by 57. Give me a decimal to the nearest hundredth.
32%.
Well, let's leave it as 0.32. But yes, 32%. All right, so now we're going to see if there's a dependence based on gender. So let's start with the females. So we're going to go with the probability that they picked math given that they were female. So remember, that would be the number of math and female over the number of females. So how many females picked math? 8. Out of how many females total? 30. Let's turn that into a decimal so we can do some comparing with it. So 2.7. We'll round to the nearest hundredth. And then the other one we have to do is the probability they pick math given that they are male. I don't want to use M again for male because I already used it for math. I got to switch it up. Well, we're going with gender, so male, female. So that's the number who picked math and are a male over the number of males. So how many males picked math? 10. Out of how many males total? Let's go ahead and divide. 0.37. So does there seem to be some dependence based on gender?
Yeah.
Yes. How do we know that? That's not what I asked. How do we know?
Oh, because they're different numbers.
So
Well, yeah, but there was 30 females.
it appears as though there is some dependence on gender. So we know this because the probabilities are different. I mean, we could go a little further if they wanted us to. It appears as though a male is more likely to pick math than a female is based on our probabilities there also. But they didn't ask us to rate that. All right, B, does it appear based on the data in this table that the preference for social studies as a favorite subject has dependence on a student's gender? Show the analysis and explain your findings. So, again, let's just start. Probability that somebody picked social studies. 19 out of 57. So as a decimal, so we'll go 0.33. So we'll do probability that they picked social studies given that they are female. So how many females picked social studies? 10 out of how many females total? 30. 0.33 again. What? So now probability they pick social studies given that they are male. So how many males pick social studies? 9 out of 27, which as a decimal?
0.33.
0.33. So does there seem to be dependence on gender?
No.
No. No. There is no dependence on gender because probabilities are the same. So instead of saying there's no dependence, you could also say that they are independent of each other. Those really mean the same thing. So there is a nice test for dependence that can be applied easily and comes from our formula for conditional probability from our last lesson and what we've been working with. Here again is that little formula that we use for conditional probability. If you have A given B, it's the probability of them together over the probability of B. So if A and B are independent, then rewrite this formula and solve for probability of A and B. So since they are independent, then the probability of A given B is the same as the probability of A. Because we were told they're independent, the conditional probability of A given B is the same as probability of A. So with that being true, looking back up here at this formula, instead of A given B, I'm just going to replace that with the probability of A. So instead of A given B, I just have A there. So now I'm trying to get this one by itself. How can I make that happen? Cross multiply. So the probability of A and B happening is equal to the probability of A times the probability of B. So if you multiply those two together and it equals the probability of them happening at the same time, then they are independent. Yes. So let's look over here. The probability that a person is left-handed is 12%. Probability they have brown eyes is 42%. And the probability that they have brown eyes and are left-handed is 2%. Is the event of having brown eyes independent of being left-handed? Support your answer. So we're going to want to use the formula we just came up with. So the probability of A and B would have to equal the probability of A times the probability of B. So I'll call left-handed my A. And I'll call brown eyes my B, just so we have a universal one. So again, what was the probability of being brown eyes and left-handed? 2%. So probability of A and B, brown eyes and left-handed, was 2%, so 0.02. Probability of being left-handed so 0.12, and then times the probability of having brown eyes, which would be 0.42. So let's actually multiply that right side. What's 0.12 times 0.42? 0.0504. Is that equal to 0.02? No. So since that is not equal, these are dependent on each other. The other way you want it, if you want to, is you could say no, not independent. Really means the same thing though. They are dependent or they're not independent, same thing. If they were equal, they would be independent. But these ones were not.
Do we need more rain now?
So probabilities involving just a single event, pretty easy to figure out. You flip in a coin, you pick one person at random, you're pulling one card from a deck of cards. Those ones are easy to figure out. It's whenever you have to do multiple steps at the same time, that's when they get a little tricky. So like flipping a coin 3 times or rolling a die 4 times. That's when you have multiple steps to it. Your probabilities are a little trickier. So given that the probability of event B occurring given event A has occurred is this. We've seen this formula. We've used this formula. This is our conditional probability formula. So nothing new with that. They want us to rewrite this formula solving for the probability of A and B. We just did this on the last page. One way we could do it is to multiply both sides by the probability of A. That would make it cancel over there. So the probability of A times the probability of B given A equals the probability of A and B. So if the two events that we are dealing with are A and are B, if those are independent of each other, then remember the probability of B given A is just the same as the probability of event B. We wouldn't have to put the given A part there. So then A times B equals A and B. So if you're trying to find the probability of two things happening, like rolling a coin and flipping a card or flipping a die, you would multiply them together. So this rearrangement of the conditional probability form is a useful tool for calculating the probability of multi-stage events. You will easily be able to accomplish this if you systematically start thinking in your head and phrasing it out using the words and or, and connecting the events that way. So here we have a spinner, and it is spun twice. Are the outcomes of the two spins independent or dependent? So if I spin it once, get my answer, spin it again, are they going to be independent or dependent? Independent. That first spin in no way is going to affect what you get on your second spin. It's still equally likely to happen. So what is the probability that you will get an even on your first spin and a number greater than 5 on your second spin? So what you have to think about in your head is we're looking for the probability of an even and a number greater than 5. That's what we're trying to get. So you got to be thinking in your head, these are an and. So you're looking for even and greater than 5. So to do that, it would be the probability of getting an even times the probability of getting a number greater than 5. Because and means to multiply our probabilities. So what's our probability of even?
4.
Out of, and then our probability of a number greater than 5?
3 out of 8.
So multiply your tops, multiply your bottoms. We get 12 out of 64, which what does that reduce to?
1/8.
False.
1/6.
False.
One.
Thank you.
Wait.
3/16.
Yeah, you know, never mind.
I was gonna say that. I was thinking it in the back
I was
of my head.
thinking .1875.
I didn't want to say it.
And then math, enter. Get you the fraction. All right, so what is the probability that you will spin a prime number and a perfect square in either order? Note that this is more complex than B. So you want a prime number and you want a perfect square, and they said the order doesn't matter. So what you should be thinking about in your head is you could get a prime and a perfect square in that order, or you could get a perfect square and a prime in that order. Order is important, but there's two orders we could have. We could have prime and then perfect square, perfect square and then prime. So to get our probability for this first scenario, the probability of prime and perfect square, what is the probability of a prime number? How many primes do we have up here?
4.
4 out of 8. And means we're going to multiply. What is the probability of getting a perfect square?
You go 2.
1 and 4 are the perfect squares on here. So multiply our tops, multiply our bottoms. We get 8 out of 64, which is 1/8. So now we got to go to the other way. Probability of getting a perfect square first and then a prime number. So we already figured out. There are two perfect squares out of 8 times our 4 prime numbers out of 8. Multiply our tops, multiply our bottoms. So we would get 1/8 for that part also. But now we have this little or statement here. We said it was going to be one way or the other. So whenever we have or in probability, that means we're going to add. So 1/8 plus 1/8. 2/8, which reduces to 1/4. So the probability of getting a prime and a perfect square in either order would be 1/4. So you had to multiply your ands, add your ors. So experiments do grow more complicated, especially when you start throwing without replacements in there. You have to keep in mind that the number you're choosing from decreases. So let's look at exercise 3. A class consists of 12 girls and 8 boys. A group of 3 is picked to give a speech. If the students are picked at random, what is the probability that all boys will be picked? So use the events below to show you how you find your calculator. Okay. So we're looking for the probability that we're going to pick a boy and a boy and a boy. So if you're picking 3 boys to give the speeches, this is what you should be thinking in your head. You're going to pick a boy first and a boy second and a boy third. So, for my first pick, what is the probability I'm going to pick a boy?
8 out of 20.
8 out of 20. Times. Now, I picked that one boy to give the speech first. What is the probability I pick a second boy? 7 out of 19. Times, what's the probability the third one's a boy? 6 out of 18. Let's go ahead and multiply. Multiply your tops. 8 times 7 times 6.
336.
Multiply our bottoms.
Here comes that. 6,840.
Let's reduce that.
Don't ever say that.
7 out of 135.
False.
14 over 285.
7 out of 135.
14 out of 285.
Are you sure? This is
Quite sure. So the multiplication property of probability is crucial in many applications in engineering decision-making stuff. So say that a power generating facility has 3 primary safety switches in case of an emergency. The probability that any one of these switches fails is 5%. What is the probability all 3 will fail given that the switches are independent? So we are looking for the probability that switch 1 fails and switch 2 fails and switch 3 fails. So what is the probability that any switch fails? 5%. So as a decimal.
0.05.
So that's going to be 0.05 times 0.05 times 0.05.
1.25 times 10 to the negative 4.
So that's 0.000125. As a percent, that would be 0.0125%. Remember, you move your decimal 2 places to the right. So is it very likely that that's going to happen, that all 3 of them fail?
Well, I mean,
Yes.
Less than 1%. It's not very likely.
There's a higher chance that you get hit by a refrigerator falling on
Probably, yes. All right, many times when using the multiplication rule, we need to be careful about how we frame the question, but if we properly frame it in terms of and or, then the rules of probability will work out. So our last problem in our notes, a company is determining the effectiveness of its warranty sales on computers. They took data on the number of customers who purchased warranties on 2 different brands of computers. If a customer was chosen at random, what is the probability they did not purchase a warranty? So what we're looking at here is we're looking at the probability that they picked computer type 1 and they decided to go with no warranty.
I don't know why you would go with no warranty.
Or they picked type 2 and no warranty. So the and, again, means we're going to multiply those together. The or means we're going to add the 2 of them together. So let's figure out the first one. Probability they picked computer type 1. 0.68. Probability they did not take a warranty. Nope. Nope. That's the ones who picked the warranty. 100.
Subtract those.
65% did not pick a warranty. So we multiply that times the 68%, the 0.68.
wouldn't it just be 0.68?
No?
That didn't pick warranty?
No. 0.68 picked computer 1. 65% did not pick a warranty.
0.442.
0.442.
Wow.
Second option, computer type 2, be 0.32. Which ones did not take a warranty? 44%. So let's multiply those ones.
0.1400.
I got 0.1408.
What? Oh, I looked at it from an angle of 0.
And then the or means we have to add those together. So do we get 0.5828?
Yes.
Or 58.28%.